video, we'll define Sylow P subgroups, and we're going to state the Sylow theorems and talk about some examples of groups where we understand the sets of subgroups really well. But before we do that, I just want to give one quick consequence of Cauchy's theorem that we proved in the last video. So when we were giving the definition of a P group, we said that a group is a P group if every element has order equal to a power of P, where that power can vary. Right? Every element has order equal to some power of P. And we said that when you have a finite group, that's equivalent to having order P to the n, order equal to a power of P. So we didn't actually prove that, and there's a reason for it. I was glossing over the fact that I want to use Cauchy's theorem in the proof. So what am I claiming? A finite group has order P to the n for some n, if and only if every element has order P to the k for some k. OK, so Lagrange's theorem proves one direction right away. If you have a group of order P to the n, then because the order of every element divides the order of the group, every element has order P to the k for some k. The other direction you can prove with Cauchy's theorem. If every element has order P to the k for some k, then you can't have an element of order q for any prime that's not P. That means that there's no prime q that divides the order of the group except P. So that shows that the order of the group has to be some power of P. So that's just one of many consequences of Cauchy's theorem, and we'll see more of those as we go. All right, so now let's give the definition of a Sylow P subgroup. This is something that we've actually seen already. We saw this on homework 2. There's exercise 9 in section 3.3, which sets up some of what's interesting about these subgroups. So we're going to take a finite group, G, and P is just going to be a prime. A subgroup of G whose order is the highest power of P dividing the order of G is called a Sylow P subgroup. So somewhat confusingly and annoyingly, this is sometimes called a p-Sylow subgroup. But I'm going to try to consistently use the term Sylow P subgroup. And let me note that if you have a prime that doesn't divide the order of G at all, then the highest power of P dividing the order of G is P to the 0 is 1. So in some sense, the trivial subgroup is a Sylow P subgroup for all of the primes that don't divide the order of G. But this is not so interesting. So when we talk about Sylow P subgroups, we're going to only talk about it in the case that P is a prime dividing the order of the group. So some notation. The set of all Sylow P subgroups of G is denoted by Syl, SYL, sub P of G. And the number of these Sylow P subgroups of G is denoted with n sub P of G. Or if G is clear from context, it'll be really common to just write NP when it's absolutely clear what group we're working with. So what does that mean? NP of G is equal to the cardinality of this set, Syl PG. This set is definitely finite because your group is finite. OK, so I'm going to pause and erase. And before I actually state Sylow's theorem, I just want to take some examples of groups that we understand well and explain what it means to be a Sylow P subgroup of that group, and then talk about the set of all of these Sylow P subgroups and the number of all of these Sylow P subgroups. Let's look at some examples of Sylow P subgroups. In Z mod 12Z, we know in Z mod NZ, there's a unique subgroup of order D for any D dividing n. So there's a unique subgroup of order D for each D dividing 12. A Sylow II subgroup has order equal to the highest power of 2 dividing 12. So that is 4. So to use this notation, Syl 2 Z mod 12Z is equal to the set of subgroups of order 4. There's exactly one. One way to write it is it's the cyclic subgroup generated by 3. So n2 equals 1. A Sylow 3 subgroup of Z mod 12Z has order equal to the highest power of 3 dividing 12, which is 3. So the set of Sylow III subgroups is there's exactly one, and one way to write it is it's the cyclic subgroup generated by 4. So N3 is also 1. So from this example, you can figure out what happens for any Z mod NZ. Let's look at A4. So this group has order 12. A Sylow II subgroup has order highest power of 2 dividing 12, which is still 4. There's a unique one. So we've looked a lot at subgroups of A4. And you can convince yourself that there is a unique subgroup of order 4 in A4. And it's the one consisting of the identity together with the permutations that are products of two disjoint transpositions. So we've seen before that this is a subgroup isomorphic to Z mod 2Z cross Z mod 2Z. So here I'm not writing it this way, but the set of Sylow II subgroups consists of this one subgroup of order 4, and N2 equals 1. A Sylow III subgroup has order 3. And there are now 4 of these. Each one is cyclic. I mean, they have order 3. They have to be cyclic. They're generated by elements of order 3. What are the elements of order 3 in A4? They're exactly the 3 cycles. So we just have to see which cyclic subgroups generated by 3 cycles are different and which ones are the same. And you can see that one way to write these 4 subgroups is you have the cyclic subgroup generated by each of these 3 cycles. Oh, there should be parentheses here. But the 3 cycle 1, 2, 3, the 3 cycle 1, 2, 4, the 3 cycle 1, 3, 4, and the 3 cycle 2, 3, 4. So what do each of these, how do you know they're different? Well, each one of these cycles has a different fixed point. Each one of these permutations has a different fixed point. So like in the subgroup generated by 1, 2, 3, 4 is a fixed point of all of the permutations. And that's not true here, here, or here. OK, so what do we see about A4? N2 is 1, N3 is 4. How about S4? So the primes dividing the order of S4, which is 24, are 3 and 2. A Sylow III subgroup has order 3. What are the Sylow III subgroups in S4? Well, they're all in A4. So why is that? Because they have to be generated by an element of order 3. But the only elements of order 3 in S4 are the 3 cycles. How do we know that that's true? We did a homework exercise on homework 1 where you showed that the order of an element in Sn can be computed as you write it as a product of disjoint cycles, and you take the least common multiple of the length of those cycles. So the only way to get an element of order 4 is to have a disjoint cycle of size 3. And then the only thing left can be a fixed point. OK, so how many Sylow III subgroups are there in S4? There's 4. We already saw them here. A Sylow II subgroup in S4 has size equal to the highest power of 2 dividing the order of S4, 24. So that's 8. And you can check that the subgroups that I've written down here are subgroups of S4 of order 8. So we have the subgroup generated by the 4 cycle 1, 2, 3, 4 and the transposition 1, 3. We have the one generated by, oh, I made a mistake here. So this should be the 4 cycle 1, 2, 4, 3 and the transposition 1, 4. OK, I got that right now. 1, 2, 3, 4, 1, 3. The subgroup generated by 1, 2, 4, 3, 1, 4. And the subgroup generated by 1, 3, 2, 4, and 1, 2. So each of these is isomorphic to D8. How would you see that? Well, you know that D8 acts on the vertices of a square. So what I claim is if you label the 4 vertices of a square the right way, like with the numbers 1, 2, 3, 4, in some order, you'll get this group. If you rearrange them, label them slightly differently, you'll get this group. And if you label them slightly differently, you'll get this group. So these are 3 Sylow II subgroups of S4. These are all of them, but how do we know that there aren't more? So I'm going to pause and erase, and then I'll state the Sylow theorems, and I'll explain what the Sylow theorems tell us in these three examples. Let's give this statement of the Sylow theorem. And we'll give it in several parts, and we'll prove each of these parts differently. So the first part says that a finite group G has a Sylow p subgroup for each p dividing the order of the group. So what does that mean? For each p dividing the order of the group, the set of these Sylow p subgroups is not empty. It says that NP, this number of Sylow p subgroups, is always at least 1. So just to say it again, you write your order of the group as some power of p times something that doesn't divide p, and there exists a subgroup of order equal to that maximum power of p dividing the order of the group. The second part says how these Sylow p subgroups all relate to each other. They are all conjugate to each other. So in the previous lecture, we saw that conjugate subgroups are isomorphic. So they are conjugates, they are isomorphic. These Sylow p subgroups are very closely related. The third part is about counting how many Sylow p subgroups are there. So we're going to write the order of G as p to the alpha times m, where p doesn't divide m. Then NP, the number of Sylow p subgroups, is congruent to 1 mod p. And this number, NP, divides m. So we write the order of G as some power of p times something that does not involve p. P doesn't divide m. NP has to divide this leftover part, this m part. And then very often, the Sylow theorems are presented in 3 parts. And what I have here is 3 and 3 star are grouped together in the same part. So that's what Dummit and Foote do, for example. Right now, I'm following the way the statements are given in these notes of Conrad on the Sylow theorems. And I prefer to separate these because the proofs are done in slightly different ways. So what is this number NP equal to? It is the index of the normalizer of p inside of G, where p is any one of the Sylow p subgroups. They're all conjugates. So this number doesn't change depending on which Sylow p subgroup you pick. So it gives us a number, a way of understanding what this NP is equal to. All right, so in the rest of this video, what I want to do is just talk about what these statements say about the examples we looked at earlier. So all the examples we saw show this first thing, that Sylow p subgroups exist. In Z mod 12Z, in A4, and in S4, we saw that for any prime dividing the order of the group, so for 2 and 3, there always was at least one Sylow II subgroup and at least one Sylow III subgroup. So what about this second thing about all the Sylow p subgroups being conjugate? Well, that's only meaningful when there's more than one of them. So in the case of A4, we saw that there were these 4 Sylow III subgroups. All of the 3 cycles in A4 are conjugate to each other. So it's also true that all of the cyclic subgroups generated by 3 cycles are conjugate to each other. And the same statement exactly is true in S4, that all the 3 cycles in S4 are conjugate, and all of the cyclic subgroups generated by the 3 cycles are conjugate. So what else did we see? We saw these 3 different subgroups of S4 that were isomorphic to D8. So those were 3 different Sylow II subgroups of S4. You can check that they're all conjugate to each other. So there's a good reason for this, but you can just check by hand that there's some element that you conjugate by to go from one of these subgroups to the other. So now let's look at this last sort of arithmetic piece, just about these numbers, the congruences, and the division. So A4 has order 12. If you write 12 this way, you write it as either 2 squared times 3 or 3 to the first times 4. N3 is equal to 4. N2 is equal to 1. So N3 is equal to 4. That really is 1 mod 3. And 4 really does divide this leftover m, which is 4. Great. N2 is equal to 1. 1 is congruent to 1 mod 2. And 1 divides this leftover part, which is 3. So when NP is equal to 1, it's sort of clear that this is going to be true. OK, so what about S4? 24 is equal to 2 cubed times 3. Or it's equal to 3 to the first times 8. Let's look at this Sylow II subgroup case. So what do we know about N2? We found 3 different subgroups of order 8. So N2 is at least 3. So what this theorem tells us is that N2 divides M. And M, when we write the order of this group as 2 cubed times 3, M is 3. So that means N2 has to divide 3. So once we've found 3 different Sylow II subgroups, we know that we've found them all, that it's not possible to have more than 3. So already, we can see that there are applications of the Sylow theorem. So in the next video, what we'll do is we'll actually give 2 different proofs of Sylow I. We'll give both the proof that's in Dummit and Foote and then the proof that's in Conrad's notes. The proof that's in Dummit and Foote is very similar in style, in spirit, to the proof of Cauchy's theorem that we gave at the beginning of this lecture. I want to do both because Conrad actually proved something a little bit stronger, and also the argument is different, and both of them are interesting. And then we'll also prove the second of the Sylow theorems, and then the other 2 we'll do at the beginning of the next lecture.